So, welcome all of you. So, today we'll start our 11th session on the course essential of oxidation, reduction, and carbon-carbon bond formation reaction and its application in oil synthesis. So, we have already covered the oxidation as well as the reduction reaction, and we are ongoing. Uh, we are studying the carbon-carbon bond formation reactions, and so, so before going to start the session, I will introduce myself. So, hi everyone. This is Vijay Rane. I'm a Prime Minister Research Fellow in IIT Delhi, and so we are here to discuss some problems. So, based on the week 11 content, which is covered by the professor in this course. So, is there anyone have any doubt regarding the topic which the reactions which are covered in the week 11? So you can let me know the any doubt if you have. So we'll discuss that one, and then so we'll discuss that one, and then we can start our session, start our some problem that I have kept here to discuss here today. So is there anyone have any doubt here? Like, if you don't have any doubt, then you can put if you can stop me in between. So if anyone want to discuss any topic, then we can discuss that one. So we'll start with our the topic that I have taken today to discuss here, which is particularly the this topic, and in which the we are going to discuss the formation of carbon-carbon bond via organometallic reagents. So you know the organometallic reagent, right? This reagent like the based on the metal and the carbon. So is there anyone have any know any examples of what are the organometallic reagents? Basically, the reagents like we have the Grignard reagent, the well-known example, right? So the Grignard reagent is also the example of organometallic reagent. Then we have the copper salts, right? Copper, let's say allyl cuprate. So that sort of reagent also we are aware about, right? So these are the some sort of organometallic reagents. So how this reagent works generally? So if you look at the electronegativity values of these elements and just compare it with the carbon, so this carbon has the higher electronegativity than these metals atoms generally. Uh, so if you look at the electronegativity values, so if you can see here, the carbon has the electronegativity around 2.5, right? And then if we compare the boron, so which is having the 2, again the tin SN, which is having 1.72, the silicon, which is having 1.7, 1.74, the copper, which have the electronegativity about 1.75, and then zinc, then followed by the aluminum, titanium, magnesium, and the lithium. So these are the metals that we are going to look at the in particularly this organometallic reagent reactions, and we'll see how these reagent are synthesized, and we can see some examples of this reagent are used in the formation of the carbon-carbon bonds. Uh, all right, so basically we'll start with the first reagent, which is the organolithium. So we'll go in in this manner. So first organolithium, then the magnesium, titanium, and see some example of the copper, the tin SN reagent, and the borate that we already know. So these some uh, organometallic reagent that we will study in this session. So first one is the organolithium. So basically, these reagent are we can see we are used in widely. So the very known example that we are generally used in day-to-day life in the synthetic chemist, that is the butyl lithium. right? Butyl lithium. So butyl lithium is like this is the reagent. So there's a 4 carbon chain, and this will be the C negative and the lithium positive. And this sort of they have the bond in between the carbon and lithium. So that's the butyl lithium. Butyl lithium or secondary butyl lithium. That also the minus Li plus the secondary butyl lithium, or there is also the third butyl lithium. And so if you look at the reactivity, this primary, secondary, and tertiary, this is the highly reactive, the tertiary. The Because if you look at the inductive fit on this one, so inductive fit direct in this manner, and that's the reason of the high reactivity, because this negatively charge is very much unstable at this position, and that's why it is highly reactive. So this is the examples of the organolithiums, and if you look at the how they are getting synthesized, so if you have the olefin, sorry, the this is the example in which the allyl lithium is prepared. So if you have such CH2 and I, then if you need to add the two equivalent of the lithium, it will produce this allyl lithium. And this allyl lithium, so it can react with the further, and you can see here. So this is, it forms like a kind of dimer. So that's the this is how the allyl lithium we can prepare. So if you add only one equivalent of this lithium, then we can able to get the allyl lithium here. And further, upon further reaction, it can further convert into the dimeric form. Further uh, example with the allyl and the alkyl halide and the lithium, and particularly in the form of lithium wire. And this generally used in the solvent generally is the hydrocarbons solvents. So you can see here the solvent here is the pentane, and it prepared the from the N-butyl chloride react with the lithium wire. In the pentane solvent, it gives the 90% of the greater than 90% butyl lithium. So this is how the butyl lithium is prepared generally. Then the third butyl chloride, if you have third butyl chloride, then 2% dispersion of the lithium, and you can get the third butyl lithium preparation greater than 60%, in the greater in the yield of greater than 80%. Then the phenyl lithium we can also prepare in the similar manner. So in this case, the solvent is the diethyl ether, and the phenyl lithium, the phenyl bromide and the lithium in the dry ether. So ether should be the dry, otherwise this phenyl lithium is getting quenched. So in all the conditions, the solvents must be the dry. So we can get the synthesis of the phenyl lithium product. So this is how the organolithium reagents are getting prepared. And if you look at the reactivity of this uh, organolithiums, so if you react this, these are the with the, let's say here in terms of the, if you react this with the aldehyde, it gives the, you can see alcohols. If you react it with the epoxides, so then it will give the again the alcohol, and reopening takes place. Reacted with the aldehyde, it gives the again alcohol. This then it react to the any organ lithium. Further, the similar reactivity with the ketone, it gives the tertiary alcohol as a product from the ketone, and with the ester group, so it react with the two equivalent get consumed, and we get the ester to alcohol with this reagent. And similar case with the acyl chloride. So when it react with the acyl chloride, then again we get the alcohol as a product when acyl chloride react with the organ lithium. Similarly, if you look at the other reactivity uh, from the aldehyde, so here. This organolithium, when it react with the uh, dimethyl formamide, we get the alcohol as a product when it reacted with the aryl lithium, sorry, any organolithium. And you can see further reactions of this. This is the example of the acid. Then this acid can convert it to into the, this is basically the salt. So R dash C double O, right? And Li. So that's like a salt. So we can get the ketone from this acid, and from the cyanide also we can get the ketone. So that's how the we can able to generate the various compounds by using this organolithium compound. Further, organolithium via a lithium halogen exchange. So this sort of reagent we can also prepare from this lithium halogen exchange. So let's say we have the alkyl halide, and if you add this alkyl lithium, so the halide exchange takes place. So it depends upon the reactivity of this R and R dash. So depends on the reactivity and the stability. So we can able to do the lithium halogen exchange reaction, and to make the from one organ lithium we can able to prepare the another organ lithium. So let's take the example of this alkynyl alkenyl lithium reagent. So if you have the butyl lithium, and we have the, if you have the alkynyl bromide, so then we can able to replace this bromo compound with the lithium. So you can see here, just need to add the butyl lithium. So here lithiation occurs, so halide get kicked out, and it forms the N bromo butane, and this organ lithium, which is the alkenyl lithium, and this further we can able to use for another reactions. Further, second example here mentioned is the, similarly, if you add the tert-butyl lithium, so in that case, the first equivalent when it react to the it do the lithiation, and then the further reaction doesn't proceed because of the bulky group of this tert-butyl. So instead of, if you want only the selectively this alkyl lithium, then we can, in this case can add the such bulky organ lithium at the starting. So here tert-butyl lithium is added, and it gives the only selectively this product. So in the first case, it was like once this alkenyl lithium is formed, it again further it further react with the n-butyl bromide, and it gives the this butyl group directly get attached to this position. So if you want to, if you have to stop this reaction, then we can replace this butyl lithium with the third butyl lithium. Further, in the similar manner, we can able to prepare the phenyl lithium. So if you have the butyl lithium in her hand, but we want the phenyl lithium. So in that case, we can able to add. So instead of this, you need to take the, let's say take here the bromo compound and add the butyl lithium to this one. So we get the phenyl lithium in our hand. So from the butyl lithium and this phenyl bromide, so we can able to provide prepare the phenyl lithium. So this all depends upon the stability of this form product. So in this case, the butyl lithium is less stable because the negative charge directly on the sp3 carbon. But in case of the phenyl, the phenyl lithium, this negatively charged is on the sp2 carbon, and also it is in the conjugation with the aromatic ring. So that's the reason the phenyl lithium uh, is the more favored, and we get the from the butyl lithium and the phenyl bromide, we get the formation of this phenyl lithium product. And also similar reactions we can perform for the different purposes. So here you can see, if you have the bromo, then you can able to convert that into the lithium. So at the multiple like the pyridine or the thiophene, that sort of starting materials. And further we can add any electrophile. So if you had any electrophile, then we can able to replace this lithium with the electrophile, and we get the our required product. So here electrophile will be here, and so in this case, if you want any sort of other electrophile if you want to add, so let's say here. So once this reaction works, so after 30 minutes probably to complete this reaction might take 30 minutes to 1 hour at minus 10 degree, sorry, minus 70 degrees Celsius. And after 1 hour, we just need to add the electrophile. And if you add that electrophile, then we can get the product. And here in this case particularly, so here the electrophile will be getting added. So this is how the we can perform various bond formation by via this method. Uh, Further examples of such lithium is the or lithium formation. We have metal lithium exchange. So that's sort of transmetallation. So if you have the Grignard reagent, particularly you can take directly the example. If you have the Grignard reagent, and here you can see the tin chloride. If you add the triphenyl tin chloride, then it gives the uh, triphenyl allyl tin compound, right? And this one, if you add the phenyl lithium to this compound, then this tin SN and C bond get cleaves, and it gives formation of the uh, allyl lithium. So this allyl lithium is get forms, and the tin PPH4 that's formed in the PPT, and that can be easily separated out. So we can able to get the allyl lithium. So the professor has already covered the allyl lithium or that sort of reaction of the allyl organocompounds, allyl stannine. So this is the allyl stannine. So this is how the reactivity of this allyl stannine with the phenyl lithium, and we can able to get this allyl lithium from the allyl stannine. So if you look at the mechanism of this reaction, so this is how the mechanism goes. So it get the some stability at this position. That's why we can able to get potentially the formation of the carbon metal bond at the different location. So here you can see the metal in this case might be the lithium or the MgX. MgX comes from the Grignard reagent. Also the zinc X or the Br2, that's the boronic ester, and any kind of the aluminum salt or titanium or the uh, this sort of metals might be there, and the L stands for the ligands. And so here in this case the titanium, the titanium isopropanol, that sort of, so that also the we can able to prepare from this sort of compounds. So if you have the allyl lithium, so if you have this allyl lithium here, then we can able to, from this allyl lithium, we can convert this into the further useful reagent. So you can see here the treatment of propane on the isobutyl with the N-butyl lithium in the dry ether in place of the timida, that's the base, and provide the conventional route for allyl lithium. So you can see here the butyl lithium needs to add and the timida and dry ether. So it gives the formation of this compound and followed by this lithium, and it gets the stability because of this chelate. And when you add any kind of the compound which has the here like the bromo compound that they added, and so this negatively charged substitute the attack on the carbon, and the bromo gets kick out, so we get the formation of the product. So here, the SN2 reaction takes place for to get the product, and you can see this carbon as a nucleophile is prepared by adding this butyl lithium and the timida. So this was the transition state, not a transition. This was the intermediate. After formation of this intermediate, the once this intermediate is formed, and then we need to add this butyl bromide. Otherwise, this butyl bromide directly react with this bromo compound. In a similar manner, Grignard reagent also are much useful. So Grignard reagent, we generally this sort of Grignards we generally use for convert aldehyde or the ketones aldehyde ketone or the acids to the alcohols or the esters to alcohols. So how this reagent is getting prepared. So to prepare this grignard reagent, there are different methods. So this was the first method, which is like the Rinke magnesium method, and in this one, the magnesium chloride and the lithium getting used, and it forms the Rinke magnesium reagent. And this reagent further, if you treat with the such chloro compound, it forms the MgCl. This was the first uh, report. And so because of this bulk, the metal being in the front in the form of highly reactive small particle, which is with the large surface area. So this is the reagent, and further there are other methods also. So if you have the from the alkyl or phenyl, if you want to prepare alkenyl or phenyl grignals, at the time you can able to add the bromo version. So in this case, the alkenyl grignal, if you want to prepare, then the bromo version of this compound, then you need to add the magnesium in the dry ether. So we can get this magnesium bromide. So it's like if you have in this case particularly, it is important to know. So although if you take the bromo compound, the resulting the grignard will be in the E and Z mixture, because the intermediate step is the formation of the uh, anion at this step, and then obviously the further magnesium can attack on the both sides. So that's why the E and Z mixture we get in this formation of this grignard. But uh, in case of the alkyl or allyl grignal formation, at the time it was the reaction is quite straightforward. So this bromo version is directly react with the magnesium, and it directly forms the grignal. And further, on treatment of this grignal with the desired ketone, as you see here in example, so this grignal reagent is directly attached on the ketone, and it gives the formation of the salt. And further, upon hydrolysis, it gives the alcohol. And if you can see the yield of this reaction, it's about 80% of the 80% yield. This reaction goes uh, quite well with the 80% yield. So this is how the utility of this grignal reagent. And further, can we also prepare the grignal from the alkyl? So in that case, so we don't really require to use as a alkyl bromide. So in this case, we can see here. So if you just add the ethyl magnesium bromide, so another and with the alkyl, sorry, the alkyl, so you can able to get the alkenyl grignard. So you can see from one grignard, as seen earlier, from one organ lithium, we can able to prepare another organ lithium reagent. So similar case with the grignard reagent as well. So here there was ethyl magnesium bromide. This is also one of the grignard reagent, and from this we have prepared the another one, that is the alkenyl grignard, and you can see the this is because the pK difference between the uh, ethyl hydrogen bond and the carbon, that is the sp2 carbon and the hydrogen bond. So you can see this sp3 carbon, sorry, this here in this case sp carbon uh, hydrogen bond has the pK 25, but this is the sp3 carbon and the hydrogen. So with this sp3 carbon and hydrogen, the pK value for this one is nearly 50. So that's why this has the higher stability compared to the sp carbon hydrogen bond, which has the 25 pK nearly 25. That's why, because less is the pK value, higher is the acidity of that proton. So this proton is more acidic compared to this proton. So that's the driving force for the formation of the alkyl grignal. Similar example we can see here. Uh, The similar this alkyl renal further we can utilize for the carry out further reactions. So depends upon the requirement. So we can able to prepare this alkyl grignal just from the grignal that we have. The next metallic reagent is the organotitanium, and so basically in this case the metal center is the titanium, and how this is getting prepared. So you need the the methyl lithium, then the titanium here. This is the starting. So the name is the titanium isopropoxide, and here also the titanium center also has the chlorine attached. So you can see. So this is the structure of this reagent. So from this chlorotitanium compound and the methyl lithium, we can able to prepare this methyl titanium isopropoxide, and LiCl forms as a PPT, and this methyl titanium isopropoxide is served as a reagent for the methyl source. So from this one, we can able to transfer this methyl to the any compound. We will see some examples. So here you can see if you have the aldehyde or the, let's say take the example of aldehyde, and we add this reagent, that is the methyl titanium triisopropoxide. So we can transfer this methyl from the titanium to the carbonyl center, and you can see here we can able to transfer this methyl to this carbonyl center, and we get the required product. And if you have the multiple center particularly in the same molecule, so if you have the molecule, so let's say this is the molecule RC. So let's take the example which has the aldehyde as well as the keto group in within the same molecule. So this is the aldehyde and this group is the keto group, right? So among this aldehyde group is more reactive towards this, the keto group is more reactive compared to the aldehyde. So you can see here, so more reactive substrate, less reactive substrate, and the selectivity. And particularly here in this case, the we have the ratio C as to B, that is the C, which is the reactivity with the substrate A, and right, because this is the R1, so R1 comes from this R1 here. So when A when this organism react with the titanium, this methyl titanium trioxide isopropoxide react with the reagent A. At that time we get the C, and when it react with the B, at that time we get the, so yeah, now it will be, now it is clear to you, right? So when it react with the A, then we get the C as a product. When it react with the B, then we get the B as a product. All right. So when it react with the, when A and B, that's the aldehyde, and here there is a ketone. So the aldehyde is more reactive. So in this case, this entirely 99.9% reaction goes to the goes on the aldehyde, not on the ketone. So it selectively react on the aldehyde. So this methyl transfer takes place selectively towards the aldehyde, not on the ketone. So you can see here this methyl is nearly 100%, right? 100% get attacks on the aldehyde. That is the here in this case is the benzaldehyde, and it gives a product formation, which is this alcohol C. So here, what the product we get from this one? The product will be from this one is the VH3. So this is the product is formed when we have the reaction with the mixture of these two, which is one is the keto and one is the aldehyde. Further, in the similar manner, so you can see here, there are now two ketones, one with the long hexyl chain, long chain, and there one is the shorter chains. So in this case, this reagent you can see here, this is the methyl, only single methyl, and you can see there are two methyl, right? So in this case also the reaction works on the center only. In the third case, there is an example of the cycloketone, but still in this case also we get the 97% uh, this cyclohexanone get reacts. And another example is the cyclohexanone and the alpha saturated cyclohexanone. So in that case also 94% of this cyclohexanone is getting react, not the alpha saturated cyclohexanone. So this is how the selectivity comes in case of this organo titanium reagent, and particularly this methyl transfer reactions. We have seen three, four examples how selectively this methyl group gets transferred from titanium to the carbonyl, and particularly the this reagent has the more affinity towards the aldehyde compared to the ketone, and also if you have the both the ketone, then at that time the more affinity toward the less substituted ketone. All right, so we have seen the titanium reagents also. The another reagent is the example is the organo cerium reagent. So basically cerium salt that we are about, cerium trichloride is the cerium salt, and how this organocerium reagent is prepared. So particularly this reagent is good for the reduction of the beta gamma enones. Uh, so we have seen such examples like, right, when we add the cerium trichloride, at that time the reactivity is different, particularly in the NaBH4, that sort of reagent. It selectively reduces the ketone sometime, or sometimes selectively reduces the alpha beta double bond. So the same cerium trichloride reagent here used, and cerium trichloride here reaction with the organ lithium. We can prepare from the organ lithium as well as the organo magnesium compounds. So we can get the RCeCl2 reagent, and this reagent you can see some reactivity of this reagent. So here in this case, if you see this example, and in which this is the ketone, that is the phenone, right? The benzophenone, and particularly when it react with the when we perform the reaction of this benzophenone with the butyl lithium, that time this halide is the iodo compound. So this phenyl ring has the iodo. This iodo get replaced when we react with the butyl lithium. But if you use this EnBuCl2 reagent, and that time we get the 99% conversion, in which the butyl group directly attached on the carbonyl, and this iodo group is unaffected, right? So this is the very good example of this. So if you add the butyl lithium here, so at that time it will give the generally in most of time. So it gives the lithiation here, and the center it's generally gets unreactive, and it gives the formation of further. It can further this. mm, phenyl lithium type compound further react with the another mole of the either the same molecule can react with the same molecule, or it can again the this reaction propagate to same molecule on this carbonyl carbon react, or again we can also get the same molecule is then uh, attack on the center, and the reaction basically gives the multiple product in hand. So instead of attacking on the this carbonyl, this butyl lithium uh, goes here in between for the lithiation and gives the formation of this phenyl lithium compound. But if you do the from this butyl lithium, if you uh, prepare this reagent, so which is the NPuCl2, and use this reagent for the on this compound, then it gives the nearly 99% formation of the product, that is the alcohol, by nucleophilic attack on the this carbonyl carbon. So you can see here some example that I have mentioned here. So this is the pentanone, and when you use the isopropyl, this metal reagent, so obviously here the isopropyl CeCl2, right? And in that case, the 90% formation of this product takes place, and this product forms in the trace amount. So how this product is getting formed? So when instead of using this reagent, the cerium based reagent, if you use the magnesium based reagent, at that time what happens? It abstracts the proton of this proton, and here it forms the, because this proton is acidic, because alpha it is alpha to the ketone, and this proton is acidic, it's getting abstracted. It forms the anion here, and further this anion attacks on the second molecule of the same compound. So you can see here it can attacks on the second molecule. So this negatively charged form here, it can attacks on the carbonyl carbon, and it gives the formation of this product, right? In which one is the alcohol and one is the ketone. And to avoid this one, we can use this cerium based reagent, and it gives the selectively almost 80% formation of this product. So without forming this product, so this product is formed in the very trace amount. So this is the utility of this cerium based reagent in the formation of the particularly the nucleophilic transformation, nucleophilic addition across the carbonyl carbons, and also in this case this nucleophilic addition results in the formation of multiple product in the first one, but not in the when you use the cerium. So if you have some other examples, like let's say if you want to selectively convert this reagent, these two, then at the time this mgx will not be helpful, and so so if you use this one, so that will not useful, but instead of this one, so if you use the Cl2, so if you use the this B reagent, so at that time, so this B reagent will be convert this group to the gives the product formation in the very good yield compared to the previous one, or also if you use the butyl lithium, sorry, propyl lithium, so that also doesn't give the formation of this product selectively. So that's how that's why this cerium based reagent also holds a significant importance. And the fourth one is the organocuprate reagents, and we are aware about the Gilman reagent, right? So the Gilman reagent we have studied a lot of time in the our bachelor's, also in masters. So this Gilman reagent also holds significant importance in the multiple reactions, and particularly because of its soft center, particularly we generally see such examples of this uh, Gilmer reagent. And so this Gilmer reagent is basically we add the copper and RMGX. So this entire entire combination, that is the copper iodide and the RMGX, R might be any ethyl, methyl, or any kind of alkyl or aryl groups. So it works as a soft nucleophile, and instead soft nucleophile, and generally RMGX is the grignard is the hard nucleophile. So if you add the copper in that one, so it will the addition of this nucleophile always takes place in the fashion of 1,4 fashion. That's the Michael addition takes place across this alpha beta unsaturated saturated carbonyl compounds. So that's the one of the classical example of such organocuprate reagent and its synthetic utility, and how these reagents are prepared. So if you look at the preparation methods, so if you have the uh, let's say allyl lithium or the allyl magnesium halide, that sort of any kind of compound, organ lithium or organ magnesium compound. So we can treat that one with the copper iodide or the copper bromide. So it gives the formation of the RCU, that is the basically R2CuM. M stands for the metal that we are using. So in this case, let's say if you use the uh, allyl lithium, so it gives the formation of these. Allyl will be there two times. That's the allyl, and the copper will be in the center, and this allyl will be twice, two times because of the valence of the copper, and this metal will be the lithium. So this is how we can able to prepare the uh, organocuprate compound, and the utility will be the same as discussed. That's the it helps to it acts as a soft nucleophile. As a result, the 1,4 addition is dominant in case of such alpha saturated compound. And further, the similar reagent can prepared from the other methods also, as seen earlier from the either organolithium or organomagnesium halide. We can also prepare from the some different methods. This is the example of the this is the R2, that might be the alkyl any group, and N. So you know the LiHMDS. So that's the that sort of uh, lithium compound, and we can add that one to the copper bromide DMS salt in the THF. It gives the formation of the R2Cu uh, DMS complex with the LiBr salt, and further on treatment with the lithium or organ lithium or alkyl lithium, it gives the formation of R2NCu R dash lithium. So that's entire complex we can able to prepare by this method. And if you look at the some examples of this one, so this is the example. So alkyl lithium with the 2-thionyl, and this is the lithiated salt, and further treated with the copper iodide. It gives the formation of the 2-thionyl copper, and this R comes from this alkyl lithium, and entire salt with the lithium. So that's the copper reagent we can able to form by this method. And if you want to, these are the basically heterocuprate, and if you want some higher order cyanocuprates, so that can be also uh, prepared by using the copper cyanide and the two equivalent of the alkyl lithium, and it gives the formation of the R2Cu CN Li twice. So that's the cyanocuprate compound we can able to prepare by this method. And obviously another class is the from the Grignard. So that's the Grignard copper reagent, and we can prepare that one from the starting from the Grignard salt. So here there is one example of the allyl magnesium bromide, right? Just the two methyl substituted allyl methyl. So that's the basically allyl group, and here it is magnesium chloride. So you can add the copper iodide here. So it will give the this allyl, and this copper will be, and this whole thing will be the twice in this case. And further, if you treated this copper reagent with the any kind of uh, where we want to transfer this entire group. So here in this case, they have given a simple alkyl iodide. So if you treated this with the alkyl iodide, so this entire group, this the carbon is the nucleophilic, and this nucleophilic carbon directly attach on the this carbon, and the iodide get kick out from this one, and it get the formation of the new carbon carbon bond here. So you can see this bond is getting formed as a new bond, and we get this bond formation in the 80 to 90% yield. So this is how we can able to prepare the organo copper reagent, and we can use that reagent as a source of nucleophile for carry out further reaction. So these are the some examples, and we can see some more examples also actually, and we'll take some more examples. So if you have, just allow me to take some more example from the book. So here is some more examples of this example of the some reactions, and particularly this cyanocuprate compound, and we can use the this sorry, the thiophene cyanocuprate, and this entirely this thiophene is the negatively charged, so we can add that one the lithium compound, and it can give the formation of this uh, organocopper reagent, in which the one is the thiophene and one is the olefin attached to the carbon, sorry, the copper attached to the copper. And so if you look at the same reagent reactivity of this reagent, if you add that reagent to this reaction, so in this case add to the epoxide, so it gives the, so this entire reagent is attack gets at on the added gets attack on the this. So this comes from the copper. So this negatively charged directly attack on the carbon, and get the formation of the product. So this negatively charged attacks on this carbon, and the epoxide opening takes place. It gives the alcohol in the 73% yield. And this entire group, obviously, this bond cleavage takes place. Give- Then only this negatively charged move, right? So this is how the cyanocuprate show the reactivity towards the epoxide. If you look at the another example here, in this case, the cuprate is the basically here the nucleophilic group is the butyl lithium, or the butyl, and this entire butyl group get transfer across the center in this fashion. So, and in the anti-fashion, because the epoxide opening, that's the reaction is the SN2, and obviously the nucleophile attack on the opposite side of this epoxide. So that's why we get the stereochemistry, anti-stereochemistry here. Right. So if you anyone have any doubt here, so if someone want to look at the more detail of the stereochemistry, how this show the reactivity toward the some sort of alpha beta unsaturated epoxide. So that will be the example of the neighboring group participation kind of reaction. So same cyanocuprate, if you react that reaction of the cyanocuprate with the alpha beta unsaturated epoxide. So in that case, what happens? As earlier mentioned, these copper-based organometallic compounds it generally behave as a soft nucleophile. So in this case, what happens? This entire R, that is the nucleophilic which attached to the carbon copper. So that attacks on the initially on the olefin, and this migration of the double bond takes place, which further opens the epoxide in the anti-fashion. So you can see here, I have mentioned here the stereochemistry particularly. So this is how the R group attacks on the olefin. Further, this double bond migration and the epoxide opening takes place simultaneously, and it gives the formation of epoxide opening. And you can see here the hydroxy group is anti-fashion to the R group. And further, if you want to prepare the epoxide at the olefin center, so we can able to get the epoxide. And obviously the with the MCPBA we know the epoxide formation with the MCPBA will be the generally seen. So if you prepare the epoxide of this one, so the epoxide will be in the syn with the hydroxy group. So if you have any additional hydroxy group, so the epoxide also will be the, so here the hydroxy group is beta, so that's why the new epoxide formation takes place in the beta direction, right? So that's the example here. So it will hold the stereochemistry, and also this sort of neighboring group participation kind of reaction takes place, gives the formation of the product as mentioned here. Also, I have mentioned earlier, so how this epoxide show the 1,2 addition instead of the, sorry, 1,4 addition instead of the 1,2 addition. So this is the one of the example I have taken from the research article. And particularly, you can see there are two alpha beta unsaturated double bonds. So this is the A and this is the B. So if you look at the reactivity of this A and the B double bond, so you can see this A double bond, which is the tertiary, and this B double bond, which is the secondary. So that is, it has the only two R groups. So in this case, it has the three R groups. And if you add this methyl, that's the copper based reagent, and you can see dimethyl copper lithium. So that's the so here this is the source of methyl nucleophilic methyl group, right? And this entire methyl group migration from this copper, so takes place around the, especially particularly only this bond, not on this one. This is because the hindered hinderedness of this double bond. You can see this double bond is tertiary, and the B double bond is the secondary. So this methyl group migrated, so attacks on the this carbon. Further, it involves in the conjugation and this in between the transition state. So if you draw that transition state, so that will be the, So this will be O negative. And in this case particularly, so as the adjacent methyl group is in the beta directing, so the addition of this migration of this methyl or the nucleophilic attack of this methyl takes place on the uh, alpha direction, that is opposite to this methyl group. So that's why we get the methyl addition on the beta alpha direction. And also this is the transition state it getting formed, and upon this goes back and it further abstract the proton and gives the formation of this product. So you can see the transition state has the double bond here, and this double bond particularly is in the conjugation with this, right? So that's not the case when methyl attacks on here, and it opens the uh, carbonyl carbon. So that time this is not the case. So that's why the particularly the methyl anion attacks on the this olefin B, not on the olefin A, and also attack in the 1,4 fashion, not directly on 1,2 fashion, and we get the formation of 91% product with the methyl attached on the fourth number carbon atom. If you look at the some example which involve the stereochemistry, so that might be I think I should show this example, which is particularly the uh, good example to show the reactivity of these reactions on the six members ring which contain the double bond. So here the same reaction, the nucleophilic methyl group will be going to add on this position, but the we need to decide the stereochemistry here particularly. So if you look at the stereochemistry here, you can see this is the carbonyl carbon, and this is the double bond which has the pi bonds. So you can see here. So in this case, the methyl is directing the alpha. So that's why the methyl attacks on the beta position, and we get the formation of product. But if you look at the stereochemistry, if the attack of the methyl takes place on the same side, that is on the alpha, so there will be the steric hindrance because of uh, this hydrogen, this another hydrogen, and again there was a methyl group also. So that's why this the methyl group, that is the parallel attack with the hydrogen, that's not favorable. And so the product that we get here, which is in which the both the methyl is the anti, not on the C, not the C. We get only the trace amount of the uh, product in which the traces of the product in which the both the methyl is the seen, but 95% the product in which the both methyl is anti. So this is the anti-parallel attack is more favorable compared to the parallel attack, and that's why the anti-product, the addition of the methyl group on the anti side is more favorable. Further, if we can, there are multiple examples of the organolithium reagent, also cuprate reagent also, and particularly uh, organochromate reagent also are generally the few examples. And organochromate reagent also have the similar sort of reactivity. Particularly, they are also a source of nucleophilic alkyl groups. So you can see, I will show some examples of such reagent. And so first of all, we need to see the how these organochromate reagent are prepared. So we know the Nozaki-Hiyama name reaction. So that's involve the organochromate reagent, and I will show some examples of this reaction. So here it is. So here the organochromate reagent is the uh, so this reagent is like not generally as like our regular that we see earlier examples. So you can see here how they are getting prepared. So if we have the chromium trichloride and treat with the lithium alumine, it gives the chromium 2 salt. And further, when it reacts with the alkyl halide, it gives the RCr 3 chromium 3 salt. So that chromium 3 further source of the R negative. And you can see here the another example here. Basically, in this case, the chromium 2 salt react with the allyl bromide here. It gives the formation of this entire group will be served as R. So this will be the R chromium 3, right? And this now can attack this is the source of the R negative now, this chromium 1. And you can see once this R chromium is getting formed, so this reaction in situ attacks on the aldehyde present in the reaction, aldehyde or the ketone, and this R negative attacks on the aldehyde here and gives the formation of the product. So you can see here. So this entire group is attacks on the uh, this aldehyde, and particularly in this case, you can see how it attacks. So basically, this bond, once this bond is formed between here, so it will be a chromium 3, right? Cr3 Br. So this bond goes here, this bond goes here, here negative charge, and via this bond, it attacks on the carbonyl carbon, right? So first step, so the how this attacks takes place, you can see, and new formation of this bond takes place from the carbon, this carbon. So this is how the uh, this chromium based reagent attacks. So there is another example here. So you can see this chromium dichloride react with this uh, it forms the react with this iodo compound. It forms the chromium 3 compound, and then it attacks on the particularly this aldehyde, because this aldehyde is more reactive compared to the ketone. So right now this entirely group attacks on the aldehyde and gives the formation of, you can see this aldehyde get reduced to the alcohol now, and you get the formation of about 94% yield of this, in which the entire this R group is attacks on the carbon of the aldehyde and get the 94% formation of this product. So these are also some sort of this organochromate reagent, and they are also getting used for the such reaction, in which the, as you see some examples here. And this is the some sort of the coupling reaction, name coupling reaction, and the example of this same uh, Nozaki-Hiyama coupling reaction. And I will show some more example of same coupling. So this is the example in which you can see so how aldehyde and the allyl iodide is coupled in the presence of chromium dichloride salt and catalytic nickel dichloride in THF, and the 4-terbutyl pyridine. It gives the 80% yield of this coupled product. So in this case, the coupling partner is the aldehyde and another is the iodo compound. So here, so this iodo compound help and the chromium chloride, it forms this chromium-based reagent, and which is the reactive towards this aldehyde and directly attacks on this aldehyde and give the formation of the alcohol. So in which this new carbon-carbon bond formation takes place by use of this chromium 2 salt. So this named reaction is called as the Nozaki Takai Hiyama Kishi coupling reactions, and yeah, basically it's the modified version of the earlier reaction, Nozaki Hiyama reaction. So this reaction is not like the our general coupling reactions like Suzuki Buchwald, in which generally is the any sort of activated uh, halo compound, and the coupling partner in Suzuki, it might be the borate or boric acid or boric acid or the boric ester. In case of the Buchwald, that it might be the any kind of nitrogen containing compound and the aryl iodide or aryl iodide. So in the similar manner, in this case, the coupling partner is the aldehyde. So which is not generally the case in the our general organometallic couplings. So this is all about the organometallic reagents. So we have seen some examples of the organocuprate previously. Before organocuprate, we have seen organocopper cuprates, organochromates. Then we have seen Grignard reagent, which is the organomagnesium compounds. Also, we have seen the organo cerium based reagent, and again after organocerium based reagent, we have seen the organo-titanium based reagent, organo-lithium based reagents. So this is all we have seen in the today's lectures, and I think we can stop here as of now. And if anyone have any doubt, then you can let me know. So I will wait for few minutes more and before leaving meeting. So please let me know if anyone have any doubt.